Video is an introduction to logarithms. There will be more videos on the topic, but this one is just to get you started. We're going to start out by defining them, and you define a log implicitly. So it has what we call an implicit definition. What that means is we don't state exactly what the logarithm is. We understand what it is from the context. So here's what I mean. If I was to say that the log of base b of x is equal to y, what I'm saying is that if I take the power b to the exponent y, that's equal to x. So we can't say specifically what the log is, but we can say that writing out the log implies the same thing as this equation. So these two equations are equivalent. Let me put in some numerical examples to make it a bit more clear. I'll start out with base 10 because that's the base that your calculator uses by default. So from here on in, if I just write log and I don't write in the base, what's implied is that the base is 10. So if I was to say that the log base 10 of 100, that's equal to 2. And what that means is that if you take 10, raise it to the exponent 2, that's equal to 100. You can verify this with your calculator. If you take your calculator, maybe pause the video now, take your calculator and find the log of 100, it's going to give you a 2. I'll just show you that real quick. So we take 100 and now press the log button, and it gives us a 2. We'll do a couple more examples. The log base 10 of 1000 is equal to 3. That's because if you take 10 and raise it to the exponent 3, that gives you 1000. So pressing the log button on your calculator gives you the exponent that you would have to raise 10 to in order to get the number that you've entered. What happens if the number is not a perfect multiple of 10? Let's say we're looking at the log of base 10 log of 99. The base 10 log of 100 is 2. We should expect the base 10 log of 99 to be a little bit less than 2, but not much. And the base 10 log of 99 is 1.996. As you can see, it's a number very close to 2, but not quite equal to 2. What that means is that if you take 10 and raise it to the exponent 1.996, that's equal to 99. Now I rounded here, so it's not going to give you an answer exactly equal to 99, but pretty close. So again, the definition of a log: the base b log of x equals y. This statement is equivalent to saying that b to the exponent y is equal to x. Understanding that this is a rearrangement of that is the purest understanding you can get of what a log is. Okay, the change of base formula. Suppose I want to know the value of the base 2 log of 32. This is easy enough. I'm going to say that that's equal to y. And then I'm going to use this rearrangement here. My base is 2. My exponent is y, and altogether that's equal to 32. I can then look at this and sort of count it out. 2, 4, 8, 16, 32. 2 to the exponent 5 is 32, therefore y is equal to 5. Because 2 to the 5 is 32, I can say that y is equal to 5. So base 2 log of 32 is equal to 5. If you want to get this using your calculator, when you press the log button, it by default gives you a log of the base 10 log. So if I want the base 2 log of 32, if I type 32 and press log, it's not going to give me a 5, it gives me a 1.5, because 10 to that exponent, 10 raised to the exponent of 1.5, that's what gives me 32. So I need what we call the change of base. The base 2 log of 32 is equal to the base 10 log, that's what the calculator gives you, remember, the base 10 log of 32 divided by the base 10 log of 2. This is a specific example of the change of base formula. Let's just try that. I take the base 10 log of 32 and divide that by the base 10 log of 2, and that gives me 5, as required. Again, because, so this is telling me that the base 2 log of 32 is 5, that's equivalent to saying 2 to the 5 is 32. Logs are defined implicitly, not explicitly. The general rule is if I want the base b log of a, that will be the base 10, or any other base, but the calculator gives us base 10. The base 10 log of a divided by the base 10 log of b. The base 10 log of a divided by the base 10 log of b will give me the base b log of a. Okay, so that's change of base formula. So let's do another example. Let's find the base 2 log of, we'll do a number that's not a power of 2. Let's say 45. So I want to know what exponent must I raise 2 to give me the value of 45. So using that change of base formula, I'm going to take 45, find its log, and then divide it by the log of 2. And that gives me 5.49. Now you can verify this. If you take 2 and raise it to the exponent 5.49, so just the first few of these that you do, maybe verify on your calculator that you're getting this right. If I take 2 and raise it to the exponent 5.49, that's going to give me 45. Now it's saying 44.94 because, again, I rounded my 5.49. If I kept more of those decimal places here, then my answer would get closer to 45. Okay, what does the graph of a log look like? Let's say I was to make our function f at x equal to the log base 10 of x. Notice this is the inverse function of 10 to the x. Remember, saying that I have the base 10 log of x is equal to y is equivalent to saying that 10 to the y is equal to x. Now, what do I get if I swap x and y. If I swap x and y, writing out 10 to the x is equal to y, I get the inverse. That's the very definition of an inverse function. You go into Lagrange notation and you swap the x and the y value. That is the inverse. An inverse function is reflection in the y equals x axis. So if I was to take 10 to the x, which looks like this, so that's 10 to the x, and I was to draw a line here where y is equal to x, the mirror reflection in that line is going to be down. That mirror reflection is the base 10 log of x. So if I'm to plot f at x is equal to the base 10 log of x, I will plot it this way here. It's going to look like this, and I know it looks like that because that is the mirror image of 10 to the x in the line y equals x. Notice this has a domain where x is always greater than 0. It's strictly greater than 0. And the range, y can be any value within the real number system. Why is my domain x is strictly greater than 0? Because that's the range of 10 to the x. And this is the inverse. So in the inverse, you swap x and y, which means you would swap the domain and the range with one another as well. I'll just show you quickly on Desmos, putting all of this together. So if I've got 10 to the x, it looks like this. And the line y equals x is here. And the mirror image across that line would go, you can see the cursor here, it would make its way up. And that mirror image is the base 10 log of x. Finally, what are uses of logs? So uses of logs are, you can do a semi-log plot, and I'll do an entire video on that. And the whole point of a semi-log plot is to take a set of data that is greatly varied and condense it down so that numbers can be compared to one another. You can also use this to compare widely varying values. So examples of that is, say, H plus ion concentration for acids. That's the pH scale, is a log scale. Intensity of sound. There's a broad range of sound intensities that you're capable of hearing. And earthquakes. So these are the three most common examples that you'd be familiar with where they have log scales. So this is the pH scale, that's a log scale. The decibel scale is a log scale, and the Richter scale. There might be an H in there. The Richter scale is a log scale. These are all based on using log functions because you have widely varying data sets, and those widely varying data sets are easier to understand and to deal with if you look at the exponent when you switch them to scientific notation, which is the essence of what you're doing when you take the log of a number. You can also use these to solve exponential equations. So logs can be used, logs are used to solve exponential equations. And if you learned anything from this video, what I hope you learned is that the base b log of x equals y implies that if you take b and raise it to the exponent y, that gives you x. These are equivalent statements. This is called the log form, and and the exponential form of the same idea. There's no explicit definition of a log. It is implied from understanding it's a rearrangement of the exponential form. And the other thing is the change of base. So if I want, say, the base, let's say base 3. So if I was to find the base 3 log of 17, I would take the base 10 log of 17 and divide it by the base 10 log of 3. So the number you are taking the log of goes on the top, and the base that you're changing it to, its log goes on the bottom. That's your change of base.